as I mentioned at the beginning of the talk, then we need a critical vesicle concentration so that we can get a single layer floating at the ocean surface to transform into a double layer floating a little bit below the ocean surface. And we get the formation of this vesicle through forces applied, which could be from the wind, which is creating waves on the ocean surface. You can also do these experiments with almost any oil, and you can shake them up and you will produce either these vesicles or these micelles, which are, I will show you in a moment. They are the same, but they don't have the second layer. So they are just one layer of spherical fatty acids. You can do the experiment with oil over water and just shake it up and you will get these droplets. And if you're lucky, if you have the right conditions, the pH and the temperature and the salt conditions, you can form these vesicles. So we could rather imagine that they would be simply made on the ocean surface. You don't have to worry too much about them. But there are some of these details. So one of them is the critical vesicle concentration to produce this double layer. And we see that this is a graph of the critical vesicle concentration as a function of carbon chain length, number of carbon atoms in the chain. And we see that the smaller chains require a much greater concentration. So there's a separation in this graph here because the very small fatty acids require a much higher concentration in order to form these vesicles. And as you go to longer chains, that concentration decreases very rapidly. When we're at 18 carbon atoms in the linolenic acid, conjugated linolenic acid, we need only 0.2 millimolar. So here at about 4 or 5, we require about 1.8 molar. And this is 0.2 millimolar. So that's 4 orders of magnitude smaller. So it's much easier to create these vesicles with longer chains. And that's good for us also because we require longer chain lengths to give the system stability under the high temperature at which the ocean surfaces were supposedly at the origin of life, about 85 degrees centigrade. Now, another factor we have to take into account is the pH stability. And this depends on what is known as the ion-dipole interaction. Because here we'll see that these are fatty acids there. This is the air-water interface. And this is at a certain pH. Well, let's start here. For example, at low pH, we have a lot of protons in the water. Means that the water is very acid. These are the protons from the water molecules. These are the hydrogen atoms from the water molecules. And therefore, at this low pH, in which we have a lot of protons or hydrogen atoms in the water, we're not going to get a removal of these hydrogen atoms, which are on this carboxyl group. So therefore, we don't have much of an interaction. We have maybe a dipole-dipole interaction, but a very small interaction between the two of them. And so at low pH, that leads to these emulsions. So this kind of a shape in which we get surface emulsions in which the system doesn't form these vesicles, which are these configurations, which have only one layer of fatty acids, or the vesicles which have 2 layers of the fatty acids, and they have a hollow interior in which water can be maintained. So at low pH, we have a lot of protons in the water, and so we don't get the removal of these hydrogens. But now as we go to pH, which is about equal to the pKa, which is the acid dissociation constant of the fatty acid, And here we're plotted on a graph the size of the fatty acids and number of carbon atoms and its pKa value. Okay. Once we get to this value, the pH in the water about this value, then we can start to lose hydrogens. And then we have this ion dipole interaction. And that gives us a rather strong interaction, which allows us to form these double layers of fatty acids. This is the ion dipole interaction. And it's maximum at the pKa value of the fatty acids, which depends on its number of carbon or its length. Now, as we go to high pH, there are very few protons or hydrogen ions in the water, so it's very easy to lose these hydrogens of our carboxyl group, and that in fact gives us two charge groups, which give us repulsion. And when we have this repulsion, we're going to form these vesicles. Okay, so this corresponds to the high pH values here. This is a plot of the volume of titration as a function of pH. So you know that as you, for example, increase the amount of hydrochloric acid in the system, we increase the acidity, but we don't go in a straight line. We go in these kind of step-like procedures. These steps are the result of exactly what's happening here, that we're losing some of these. We're changing the background pH by losing or gaining hydrogen ions to our system. So what I want to say that for these very long, which we needed for the temperature, remember, and also to produce these critical vesicle concentration, we need the very long carbon chain fatty acids. But the problem is that they have a pH stability at around 9, let's say, for conjugated linolenic acid. And a pH of 9 is really too high. We, in fact, expect a lower pH than neutral for the ocean surface at the origin of life. That is because of the carbon dioxide in the atmosphere, which can produce carboxyl acid, lowering the pH to maybe 6 or between 6 or 6.5. So that's a problem because we won't have pH stability for this size of fatty acid. But one thing I didn't mention is that the fatty acids can align themselves side by side. So this is the single fatty acids, but if we have two, they can actually overlap here, and especially where there are these double carbon covalent bonds. And that makes the system more stable. But also, sorry, but also if we have a system of these long chain fatty acids with the conjugate double bonds, and they overlap, they come close to each other in this way, under UVC light, we can form a covalent bond between the two. This, in fact, happens with temperature also, or also with just time. After these have been, the interaction between them, sufficient time, we can all of a sudden get a covalent bond formed between the two. And in this case, what we're doing is we are reducing one of these conjugate bonds. So we go from 4 conjugate bonds here to 3 conjugate bonds. So if we form this covalent bond between the two, then we will get a shift in the wavelength to absorbing at a shorter wavelength. But the good thing about that is that we are becoming stable over pH values. So here in A is the case in that we don't have any cross-linking. It's called, this formation of this covalent bond is called cross-linking. we don't have any cross-linking, then we get all these problems with the pH, and then we won't get these vesicles being formed. But if we have sufficient cross-linking, then we can show that the vesicle is stable at all values, almost all values of pH. So it no longer becomes a problem. And of course, it is much more rapidly produced, this cross-linking, with UVC light than it is with temperature. But that's why, for example, it's not a good idea to store your cooking oils, like olive oil, at high temperature, because the omega-3 can form these double bonds. When we say omega-3, we're talking about 3 carbon atoms from the tail. We start the conjugation. So we can reduce the conjugation by forming these covalent bonds. So we can convert, for example, omega-3 into omega-6. We can also get migration of these bonds along the chain, depending on temperature and depending on light. And that's why the bottles, for example, of olive oil are also obscured. They're dark, so we don't get light, and you should store them in a cupboard away from light if you want to maintain the omega-3 in the oils. So this is to show that even though the pKa values of these long chain hydrocarbons, when they're conjugated, is very large, so about 9, we can get stability even at low pHs like 6 or 6.5 if we have cross-linking between the chains, which will occur as long as there are ultraviolet light. Or temperature, high temperatures also can do that. So when we have 85 degrees centigrade, we're also going to get some cross-linking. Now there's still one more problem, which is known as salt flocculation. And this flocculation consists of these fatty acids sticking to the salt through electromagnetic interactions. For example, the calcium from calcium carbonate, calcium 2+ ions, they will stick and they will form like globs of material fatty acids with the calcium ion, and they will form big globs and not be able to form these vesicles. But we can also see that with cross-linking, we increase the amount of salt at which we will lose vesicle stability. So in this graph, we've plotted the vesicle stability, okay, for the system as a function of concentration of these calcium ions. So for example, for conjugated linolenic acid, we can have up to a concentration of about 220 in these units, milligrams per liter of calcium ions. Now, if we allow cross-linking by heating the system, this is an experiment that these guys did, heat the system to 50 degrees centigrade, and then we can see that we have vesicle stability to about 310 milligrams per liter. And if we do the cross-linking at 70 degrees centigrade, then we can have even greater concentration of salt. So this cross-linking through UVC light also makes us more stable. And it's also interesting to note this is the same, but these are for the same acid. That means 18 carbon atoms, but without cross-linking, without conjugation. Sorry. So this CLA means conjugated linolenic acid. This is just linolenic acid. We see that with conjugation, we also get greater stability, vesicle stability. So this is the conjugation that we find here, and the number of double covalent bonds here conjugated. So the greater the conjugation, the more stable, also with respect to salt. Now, how do we get encapsulation? Well, as I mentioned, if there are other organic molecules at the ocean surface, and we said that the density of organic molecules is very high at the ocean surface, then it would be very probable that, or it could be quite probable that, for example, DNA or segments of DNA could be trapped within the system. Or we could just have hydrogen cyanide in the water, and it filtrates into the system, and then through the ultraviolet light we get the production of DNA. But we will get at least some organic molecules trapped inside the system when it forms this vesicle. And it's been determined that with calcium 2+ ions in the system, this is actually a molecular dynamic simulation. So the 2+ ions, the calcium, are these white dots, and this is DNA, and this is the double layer lipid. And without these calcium ions, the DNA does not attract to these double lipids. But with the calcium ions, it provides an affinity, and we get the DNA sticking, which in this case would be sticking to the inside of this double lipid vesicle. And if the DNA is close to the vesicle, then even if the fatty acids in the vesicle didn't have a conical intersection, as I mentioned in the previous talk, we could have energy transfer from the absorption in these fatty acids utilizing the conical intersection of the DNA to dissipate to the ground state. So we could get this energy transfer as long as the distance is not too great between the DNA and the fatty acid vesicles. So if these fatty acid vesicles are, these fatty acids are absorbing photons, then they can dissipate even if they don't have a conical intersection. They can dissipate through DNA. So again, the system, the two systems itself would be a greater dissipating than the separated systems. And that's what we have to show, that always we get an increase in dissipation as we go through complexation in life. So we can have this energy transfer, and we therefore get greater dissipation. The system is greater dissipating than the two components independently. And also because the vesicle and the DNA or the other organic molecules within the vesicle are absorbing UVC light and dissipating that into heat. And as you know, these lipids are really like fat layers, so they are rather impermeable to infrared light. So they block infrared light, so we could get a buildup of heat within the system. So we could have this UV tar process of replication. Remember, this is the replication of DNA without the complex enzymes which exist today. This would be the physical mechanism for replication of DNA at the origin of life, and of course it's related to dissipation also. But as the surface temperature is cooled, then without the absorption of a sufficient amount of light, the interior of the cell, this is the protocell, would not warm up enough to have this denaturing. So these vesicles would help for denaturing. So the first protocells, then we could imagine, were made up of at least 18 atoms, carbon atoms. And they were probably, or at least some of them were aryl acids, which have 4 conjugated bonds here, starting from 3 from the end here. This is instead of N, they put omega. So this is, for example, an omega-3 acid because it has 1, 2, 3 carbon atoms before the conjugation. And they were probably converted through cross-linking. Remember, when we have cross-linking, then we lose one of these conjugations. So they were probably converted into linolenic acid, which has 3 conjugations, and then would be absorbing at about 270 nanometers, close to the peak in the UVC light, which was arriving at the Earth's surface. But it was probably not only these 2 fatty acids. For example, today in the cell walls of all organisms, there is not only one type of fatty acid or one type of phospholipid, but in fact, many different types combined. So we can have all of these different types combined here. But the tendency would be to produce these with 3 conjugate bonds, because this is where the light intensity is greatest. And this is where therefore dissipation would be greatest for the system. So we have this cross-linking, which is going to reduce this parinaric acid to linolenic acid. They're both the same length, they just have a difference in conjugation. And we get this overlap of the 2 tails, especially around the conjugated part. And that would give rise approximately to a spherical protocell of about 50 nanometers in diameter, with a wall thickness of about 3 nanometers. So this is not the scale, but these are the values that one would expect to be most likely with this size of fatty acid. But of course, there would be a whole distribution of ranges. That's one thing we are looking at now with the work of Ivan, who I hope is going to talk in the following hour a little bit about his work with strong coupling of light to the DNA within inside this vesicle. This is just an example of linoleic acid. Linoleic acid has only 2 conjugate bonds. I didn't find one of linolenic acid with 3. So we'll just look at the example of linoleic acid, and that gives us this diameter size of about 50 nanometers and a wall thickness of about 3 nanometers. Now, what does the fossil record show? Well, going back to the origin of life, there's nothing to see. But if we go back to, let's say, the mid-Archean, at about 2.7 times 10 to the 9, or I'm not sure if this is the date in years, I guess. 2.7 times 10 to the 9 years. Then if we look at these gas chromatograms, so what we do is we take a sample of these banded ion formations. Remember that these banded ion formations were laid down during the Archean, and they are basically ferrous ions which have been oxidized. And that's where we get the iron today from. So these banded ions come from the Archean. And if we take some of that material and then heat it up, some of it will become volatile and will escape. And we can put it in a system which is called a gas chromatator. And that system allows us to measure the times of movement, or the velocity of movement of these different particles in the system. So and they have a surface within, let's say it's a cylinder, they have a surface within the cylinder which has some affinity to these molecules. So for example, the larger molecules will have greater affinity, so their velocity will be slower and they will take more time to traverse the path. So that's how we can distinguish the size by the affinities to some of them will be trapped by the surface and then allowed to move on again, and then trapped and allowed to move on again. And the larger the chain, larger the number of carbon atoms in the chain, the greater the affinity, and so the slower the velocity of the system as it's moving. So we can separate out the different lengths. So we find here in these banded ion formations that we get carbon atoms of around carbon fatty acids with carbons of about 18 carbon atoms in size, and also 16 and 14. We see that again in different regions, that the 18, sorry, carbon atoms, but also we get larger fatty acid chains. So the fossil record is indicating that we do have certain evidence that the fatty acids were large at the origin of life. And they would have to be large in order to maintain themselves integral at the high temperatures and low pH values. So in conclusion then, we have a UVC dissipative structuring of fatty acid vesicles in water which is saturated with carbon dioxide or carbon monoxide. Under this UVC light, we can produce ethylene, and this ethylene by removing a proton here, we make it into a radical, and then it can grow in size. And so in fact, starting with ethylene, we can produce these other hydrocarbon chain lengths. And in fact, we see that in the register, they're all like even numbers, you know? 24, 22, 20, 18, 16, so on. So they're all even. So they all seem to be produced from these ethylene groups here. And then after the extension, we could have an oxidation process induced by ultraviolet light also to produce this carboxyl group. And then a removal of a proton, which gives us double bond at arbitrary positions, but then migration of the double bond to lower the Gibbs free energy into this conjugated form here, which start absorbing then out around the peak at the 260 nanometer peak in the spectrum, which is arriving at Earth's surface. And through covalent cross-linking between different fatty acids, we can form a stable system at low pH values and at high temperatures, about 85 degrees centigrade. So we're given more or less the dissipative structuring of fatty acids and their formation into vesicles, and how, most importantly, how these vesicles, along with the other organic molecules like DNA, would have helped to increase the dissipation of the photons arriving at Earth's surface. So we call this the dissipative structuring, not only of the fatty acids, but also of the vesicles. So I have sent you all a paper, which you can find on your email, the last email I sent you, that I wrote with a student of mine, Oscar Rodriguez, concerning this in more detail. You can find many of the details. And we published this in the Revista Cubana de Química, because there was a conference in which we gave a talk on this fatty acid production in 2019 in Cuba. Okay, are there any questions?
Yes, I have one, Caro.
Yes, Ivan.
It's from the beginning, I think. Just how many light absorbs these fatty acids in comparing with DNA?
Oh, yes. This one here, no? This is the molar extinction coefficient for these fatty acids. So they are quite large, no? Because for DNA, I think we're around 15,000 instead of 70,000. So maybe even as high as 5 times as much than DNA. I initially thought that DNA was the greatest absorbing organic molecule in this wavelength range, but it turns out these fatty acids have even greater. So probably these fatty acids would have been around, floating on the ocean surface, and DNA, because we don't know exactly yet how likely it is that we will get the right conjugation. No? So we could have different conjugations giving us different absorption at different wavelengths. I think this is for the absorption at 270 nanometers. I should have included it here. But for some of the other wavelength absorptions, this could be lower. But what we require also not only a large water extinction coefficient, but also that we get rapid dissipation. And so for some of these others, which maybe don't have a conical intersection, they could use the conical intersection of DNA, transferring the energy here from one to the other so that we can dissipate into heat through DNA. Did I answer your question?
Yes, I think I need to add the absorption of the vesicle in my simulations.
Yes.
I'm using almost nothing of absorption for the membrane, but I think it will affect the results mainly in the shorter vesicles. Maybe when the vesicle is greater than 100 nanometers, maybe the absorption of these fatty acids are not going to change very much the result.
Okay, well, it would be very interesting to find, there's so many variables, so it's very hard to say which would be correct, no? Which variable would be most important, whether it's the conjugation or which one of these conjugations give the most dissipation. But we need stability first, so it has to be conjugated. And we need absorption. So, and around the peak is the B is here, which is about 270 nanometers. Just a little off from the peak here.
Yeah.
This is the kind of absorption spectra that you would have to include. Of course, you could also just simulate it, with a square pulse here. Just say like it's between 250 and 290, for example, just a square pulse, just to simplify the calculation.
Mm-hmm.
Because there's so much involved that it'd be hard to give any. We could not hope to give something quantitative, but we could give something qualitative.
Yeah, and also I'm having a little problems while going to lower wavelengths.
Okay.
I don't know. I have to work more. I paused my work in this project because I'm finished the semester.
Yes, I imagine you're very busy, with exams.
Yeah.
Studying. Yeah, don't worry.
Yeah, but I take note of this.
Okay. Ricardo told me that he probably knows somebody who is inscribed in the Sociedad Mexicana de Física. So he's going to help. If you could send the forms that they have to sign to him.
Okay.
That would be great, no? Ricardo, no, Esmeralda hasn't answered you yet, I guess, no?
Yeah, she didn't answer me yet.
Okay, I'll try
I
to
will answer.
her also so that we have possibility. Okay, but any other questions on the talk that I gave today?
Sí, Ricardo, estaría bien. Gracias.
Is anything that was not clear? Please ask me. Ivan, do you have something to present?
Me or somebody else?
I thought maybe you would give a little bit of talk about what you would.
Yeah, I don't have any slide, but I can show my Python notebook
Okay,
and my graphs and the draw I sent you last time.
okay, then, yeah, that would be all right. So we do that in the next hour, no?
Mhm.
At 6 o'clock. Okay. So just a few minutes, and so the others know basically what you're doing and what is strong coupling.
About that, after doing the simulations and thinking a little about it, I think we're not reaching the strong coupling regime in this interaction, but because the strong coupling arises when the normal modes of the cavity superpose with the excitation of the molecules. I don't think we're having that phenomenon.
Maybe it depends on the size, no? Or if it's spherical or linear.
No, it works in planar cavities.
Okay.
But I don't think this is the case, but we are in the weak, strong coupling. But I think it's enough to show something interesting.
Okay, yes, I think so. And also, you know, we have this possibility of focusing the light, as the article that I sent you recently, no?
Mm-hmm.
I don't know if you would call that strong coupling. Maybe that also has something to do with strong coupling, no? Focusing.
Firstly, I think in strong coupling because I read some papers about strong couplings of bacteria and other photosynthetic molecules. Well, the bacteria is not a molecule, but the chromophores of the bacteria. So I think I thought that time that maybe something similar could occur with DNA, but I don't think that's the case. But the interaction that we have between the cavity and the DNA, I think is enough to the work. Mm-hmm.
Yes. Yeah, I think so. So why don't I finish this session, and then you give maybe 10 or 15 minutes talk with some questions, and we'll continue discussing at 6 o'clock. Is that okay?
Okay.
So don't go away. Stay close to your computer, because at 6 o'clock, Ivan is going to give a small talk about what he is investigating and what he has found so far.